something that will produce H plus, right, or hydronium. Okay, everybody remember that our proton, or H plus, is the same thing as this, right? This just is solvated with water. Okay, so Arrhenius said that an acid must produce H plus in aqueous solution, right? Okay, so when we think of an acid, we think of this, right? Okay. What about a base? What did he say that the base would produce? What do we think of when we think of a base? Okay, hydroxide. So not just OH, which is close, but the OH minus, right? Okay, so produce, and these would be in aqueous solution. Okay, our Bronsted-Lowry theory. Okay, so this encompasses more of our acids and bases. So our first theory worked for some, but we really need to elaborate on that theory. So the Bronsted-Lowry theory stated that an acid is a proton, okay, which is the same thing as this H plus. It's a proton donor, and a base is a proton acceptor. Okay, so we followed this Bronsted-Lowry definition, and we were able to predict some products, right? Where we would donate a proton, okay, and then we would form, if it was an acid, we would form the conjugate base, and the base would form the conjugate acid. So we were able to pair those up, okay, and look at what's our conjugate acid, conjugate base. Okay, if you have a strong acid or base, that means it completely dissociates. Okay, this is what we're going to elaborate on today. Okay, so that means that if you take, let's take HCl. Okay, has everybody got your strong acid, strong base list out? Okay, if not, you'll want it. Okay, and I passed around another little list here if you're just coming in. Go. Anybody else need this? Did you get it? Okay. Okay, so what this means, if you have a strong acid or a strong base, when I say completely dissociate, that means that we have a single reaction arrow, meaning that in water we produce only the ions, our conjugate acid and conjugate base. Okay, so if we were to draw our products, we want to predict our products. Okay, so the first thing we want to do is label acid and base. Okay, so which one is our acid? HCl, right? And it's common to us. We've used it in the lab. Okay, is it strong or weak? Okay, look again at your list. Okay, so this I'm going to put SA for strong acid. Okay, and then the water has to be the base. Okay, if we follow the Bronsted-Lowry theory, an acid donates a proton or a hydrogen. So in this definition, it has to have a hydrogen, right? So you can, look for that as well. Okay, so if it donates a proton, okay, what happens to our HCl? What does it become? Okay, not just Cl, but exactly, chloride, so Cl minus, because it's neutral and it lost a proton, which is positive. Okay, so we form Cl minus. So this is acid. This is our conjugate base. Okay, if H2O picks up a proton, what's it going to form? H3O plus. Yeah, and that's called hydronium. Okay, and that's a conjugate acid. Okay, if we look at our strengths, okay, our relationship here, we have a strong acid, so its conjugate base is going to be weak, right? Okay, good deal. All right, so we're going to be using this a lot today here in a few minutes. Okay, before we get to more on this, we're just going to talk about some trends in the strengths of acids. Okay, this takes some going back over. Okay, I'm going to try to make it as simple as possible. It's not that it's hard, it's just you have to memorize the trends. Okay, and this is not a huge part of your exam, okay, but it is, a small part. And it really does help. So when you get to, if you go on and take any more chemistry classes, it helps you to be able to, you know, look at an acid or a base and kind of determine, is it strong or weak. Okay, we're only going to look at binary acids, and all that means is that we have two different atoms. Okay, so binary, that's all that means. Okay, if you look at your hydrohalic, okay, that sounds maybe a little complicated, but all that is talking about is if you have a hydrogen bonded to a halide or a halogen. Okay, so group 7, everybody agree that's our halogens? Remember that from Chem 111? Okay, so that's all that this trend's talking about. So we're looking at a hydrogen bonded to one of our group 7 nonmetals. Okay, so so we have HF, HCl, HBr, HI. So you see all those in group 7 there? Okay, the trend is, okay, the stronger the bond, the weaker the acid. Okay, but what we're really concerned with, well, let me say something else about that. Okay, let's do this. Okay, HF has the strongest bond here. Okay, so this bond in between this hydrogen and fluorine is very strong. Any guesses why it would be strong? Fluorine is the most electronegative atom, so it's pulling really hard on those electrons. It's also small, okay? So the smaller and shorter a bond is, the stronger it is, which makes sense because they're closer together, okay? And so our fluorine there, this HF bond, is really strong, okay? So what's an acid supposed to do in water in our example? It's supposed to, the Bronsted-Lowry definition says that it donates a proton, right? Okay, so if this bond is really strong, is fluorine going to want to let go of that hydrogen? No. Okay, so the stronger that bond, the weaker the acid. Okay, so that's why. Okay, the more readily that a acid will give up a proton makes it a better acid, right? Because if it will donate its proton instantly, then it makes it a better acid. It's a stronger acid. Okay, so the stronger the bond, the less acidic. So this is the main thing we're looking at here. So if we look at our group 7, okay, HI is a better acid or stronger acid than HBr, than HCl, than HF. Okay, so the stronger acid is down towards the bottom, however you want to memorize that. The next slide, which I'll show in a second, is basically the same thing, but it's for group 6. Okay, same idea. So if we look over at group 6 where we have oxygen, sulfur, selenium there, it's going to be the same idea. So the lower down on the periodic table, the weaker the bond. Okay, and so as you move up, okay, you're going to get a weaker acid. Okay, so the lower down on the periodic table, the more acidic. Okay, so HI is more acidic than HBr, than HCl. And I think I give you, okay, you don't have values yet, so we'll look at those later. Okay, so this is what I just said. So something like H2O has a stronger bond than something lower down on the periodic table with hydrogen. Okay, and so your acid strength is the same trend as for group 7. If it's lower down on the periodic table, bonded to a hydrogen, of course, okay, then it's going to be more acidic. So see, this is greater here. Okay. Okay. When we take one of our hydrohalic acids, meaning just a hydrogen bonded to an halide, there's something called a leveling effect. Okay, and all that means is that in water, okay, that's the key word, in water, okay, the strongest acid that can be formed is H3O+. Okay, so if we think about, okay, HI, so is it a stronger acid, what we just went over, than HCl? Is this stronger than HCl, HI? Okay, y'all didn't understand the trend. Do I need to explain the trend again? Okay. Okay, stronger acid. What did I say? The further down on the periodic table that you go down, the stronger the acid. Okay? All right, so HI is stronger than HCl, okay? But if you look here, does everybody agree with this equation here? Our HI lost a proton to form this. Our water gained a proton to form this. Okay, well, look at HCl. Okay, the only difference is that halide, right? You've got a iodine versus a chlorine. Okay, but the acid that you form is H3O+, no matter what. Okay, so this is called the leveling effect, whereas in water, HI, HCl, HBr, they all have the same strength in water. Okay, and that's just because H3O+ is the strongest acid you can form in water. So if they both completely ionize because they're strong, there's really no difference. So that's why in lab, you know, we can use HCl. It's easier to handle, easier to deal with, cheaper, and it's in water not going to make a difference. It's still going to be as strong as HI or HBr or HF. Okay, so just to demonstrate that again, here's HBr, same thing. Okay. So if it completely ionizes 100%, we still form H3O+, right? That's the strongest acid. That is an acid, right? That's our definition. Okay, so in water, they're the same. Okay, and that's just called the leveling effect. Okay, however, when you look at values for acidity, and we'll look at these later, okay, you're going to see HI, and it's going to have a more acidic value. Okay, and that's because this is only true in water. Okay, if we start using other solvents, okay, then it's different. Okay, so this is what we do in organic. We don't use water very often. Okay, so you can use, you know, acetone or in different, you know, ethers or acidic acid or anything that's non-aqueous. Okay, then the leveling effect doesn't apply. Okay, so you're going to see that difference. You're going to see HI being more acidic, and it's going to produce more acidic ions than HBr, HCl, or HF. Okay, but in water, they really have the same effect because H3O+ that's the only thing that's the strongest acid you can form in water. Okay, so here's the example I already put on the board. So it's a strong acid. It produces H3O+. So in water, it's essentially equal to HI or HBr. The same is true for a base. So hydroxide is the strongest base you can form in water, right? Because you have water. So if it loses a proton, okay, then you get OH minus. Okay, so here's the base there. Okay, and our H2O is the acid. Okay, and so the same thing applies. So if you have a base that reacts with water and forms hydroxide, then you're going to see the leveling effect. There's not going to be a difference there. Okay, and this really all goes back to water being able to donate and accept protons. So you're really, you know, here we're accepting, it's acting as an acid. There it's a base. And so we're always forming hydroxide or H3O+. Okay, so there's nothing else that can be formed there for the acid or base. Okay. This is just a table that you can look at and, you know, be sure that you see how it works. But here's your acid, and then over here is the conjugate base. Okay, so this just goes back to our strengths that we already looked at. Okay, but this is a great practice. You know, cover up one column or blank out a couple of these and be sure that you can draw the conjugate base, you know, or the acid or vice versa. Okay, and so as you see, so look up here. Okay, so what acid is this? Look at your table. Looks like it's strong. It's at the top. Does everybody see it? Okay. It's on your strong list, perchloric acid, and so its conjugate base is going to be very weak, right? Okay, and so as we move down here, so here's acetic acid, Okay, so we're getting, weaker and weaker. Okay, technically we call ammonia a weak base, right? Okay, so here it's so weak that it's technically really a base. Okay. And if you look at it in reverse, so let's say I gave you a base. So this is a strong base now because its acid was very weak. Okay, you can look at it in reverse. So a base is going to accept a proton, and it would form the NH3 there. Okay. I want you, I know it's probably been a while, but to try to draw the Lewis structures for these two compounds. See what you come up with. I know these are hard, so I just want you to see and get the point here in a few seconds. So there's the perchloric acid, and then you have phosphoric acid there. Okay? So just try. See where you would, even if you don't want to count up electrons, just try to think about how it would be arranged. What would be bonded to what? Okay, what's your central atom? How is it going to be bonded? Okay, these are both acids. You don't have to necessarily do the NASB. Just try to arrange the atoms. What would you connect to what? Okay, what I want you to see is it's a very common mistake to try to, what most of you are probably going to do. So, yeah, just try. It's not grading it. Just try. Okay. For those of you that don't have the notes, just try. Okay, how many of you, because of how it's written, that's what I'm going to show you, it's confusing. It's written as HClO4 with the hydrogen first. Okay, so how many of you bonded the hydrogen to the chlorine? Most people? Okay. That is a very common mistake. We didn't do even ones as hard in Chem 111, so I wasn't expecting everybody to get it right. The other thing is normally, chlorine, when I see it, I think, it's going to make one bond. It wants to be like argon. So it's already kind of doesn't obey our octet rule. I mean, it still has 8 electrons, but normally it's not going to want to make, 4 different bonds. So I wanted you just to try it just to see what I was talking about here. Okay, the hydrogen is bonded to an oxygen, okay, not to the chlorine. Okay, so this is what it looks like. And some of you may have tried to draw like a double bond there. I think you were maybe trying that, and that would be a thought. Okay, and the same here. So the phosphorus is in the middle, and it is one. Phosphorus can make more bonds than what you would even think. It can even make 5 bonds. So that doesn't surprise me too much. But then here's your hydrogens. Okay, so they're bonded to the oxygens. Okay, so this next slide basically just says that. Okay, that it's very common for students to not realize that the hydrogens are attached to the oxygen atoms in what we call ternary acids. Okay, so we looked at binary acids just a few minutes ago, talking about HCl. Okay, the hydrogen and the halide were binary because we had two. Okay, well here we have three different atoms, right? We have a hydrogen, chlorine and oxygen, or a hydrogen and a phosphorus and an oxygen. Okay, and we write it like this so it's confusing. Most times we write things to make more sense. I think you asked the question the other day and asked why it was written that way, and I said because that's how you draw it. So usually that's what we try to do. Okay, so these are a little bit confusing because that's not the case. Okay. All right, so ternary acids. So there's a big, long thing in your book, and basically I'm going to try to break it down to something pretty simple. Okay, when we're trying to look at ternary acids, meaning we've got three different atoms and trying to determine the strength, okay, you're going to look at the number of oxygens. Okay, so there's a whole long spiel I could go into on exactly what's going on. Okay, but if a acid, the more oxygens it has, the more acidic. Okay, that's really what it comes down to. So I'm going to give you a little background information, but the more oxygens equals more acidic. Okay, when you add oxygens, it increases the oxidation state. Okay. And just like our binary acids, if you have more oxygens, it weakens those bonds. Okay, remember, the weaker the bond, the more acidic. Okay, so it all kind of ties in together. Okay, and you increase the oxidation state of the central atom. Okay, so for every additional oxygen atom, you increase the oxidation state of the central atom by 2. Okay, so what I said here, the more oxygens, you increase the oxidation state, and make it more acidic. Okay, so let's just look at this. All right, first off, look at your acid-base list. Okay, and look at the first two listed there. Which one's on your strong acid list? CH10, which is what? Nitric acid. Okay, is nitrous acid on your list? HNO2? Okay, that's because having that one extra oxygen, you have 3 oxygens versus 2, makes nitric acid much more acidic than nitrous acid. Okay? Okay, look over here. Do you have sulfuric acid, H2SO4, on your list? Okay. Do you have sulfurous acid, H2SO3, on your list? No. Okay, so that one extra oxygen, the more oxygens, the more acidic. Okay? All right, so here's an explanation. Basically, it has to do with, well, actually that was on the previous slide, just with increasing the acidity by decreasing the bond strength. Okay? Now look at these two. All right? So we've got HBrO4, bromic acid there, okay, and we have HClO4, okay? Which one's on your list? Okay, what's the name of it? Okay, is this one on your list? Okay, but they both have 4 oxygens, so how do we tell the difference? Okay, and the reasoning is that chlorine is more electronegative than bromine, and it makes it a better acid. That's just something you have to, study and look back at if you don't remember it after today. But remember, fluorine is our most electronegative, right? Okay, so if we go down, whatever's closest to fluorine is more electronegative. So the chlorine's first, and then the bromine. Okay, so if you have 2, or you have the same number of oxygens, you look at this atom here to see which one's more electronegative. Okay? Okay, and this just shows it again. So there's actually, this can get real confusing, the names of different acids. You have to be really careful when you're in the lab that you're using the correct one because their names are very similar. So we have perchloric acid, which we said was strong, right? On your list. It has 4 oxygens. Okay, so there it is right here. has an oxidation state of 7. Every oxygen that was added increased the oxidation state by 2. Okay, then we have HClO3, which we already said was not on our list, right? Okay, and then there's just chlorous acid. So there's all different names for these. So you have to be careful, be sure that you select the right one and read the labels carefully. Okay, and this one is next because it has 3 oxygens. This one comes next because it has 2. And then the weakest acid would be this one here. Okay, and this is actually a component that's in bleach. Okay. That's it for the trend. So you just got to, like I said, look back. Remember that's for your binary acids and your halides, group 6 and 7. The lower down the periodic table that your atom is or your halide is, the more acidic. Okay, and then when we have the oxygens, the ternary acids, then we look at how many oxygens are there. The more oxygens, the more acidic. Okay, in Chem 111, we talked about neutralization reactions. So you've done this whether you realize it or not, or you may have forgotten from Chem 111, but you've done lots of neutralization reactions. So if you were in my Chem 111, we did at least 2 titrations, if not 3. You were neutralizing your acid, okay? And so at the end, you had salt and water, right? Okay, and so we were able to put that down the drain, okay? And so we use this a lot in our lab to prevent waste. I think I mentioned that just by taking, especially in organic, last week we had a pretty strong acid, but we had this big bath of baking soda, and we just, instead of having to dispose of the acid, it's very corrosive, it's going to eat away at the bottle and that we put it in and everything else. So we put it down in there, neutralized it with the baking soda, it fizzes up and then settles back down, and once it's settled, it's salt and water, so it can go down the drain. All right, so that was our simple definition, yes. Do what now? Yes. Mm-hmm. Yep, so if we have, actually a guy got a little acid on his finger, and he's like, my nail's kind of feeling numb. I was like, okay, well, let's wash your hand, whatever. Then we just took baking soda and just put it on his nail and rubbed it around and rinsed it off, and he was good to go. Okay, now here's our definition now. So that was a simple definition, and this in bold we will keep coming back to. And when you truly understand this definition, you'll be able to do the rest of what we're going to do for this chapter. Okay, so let's start by just breaking down what this definition says. Okay, it's basically saying what the previous one says, okay, but it's just a little more complex. It's more detail about it, okay? So first of all, what is a salt? Anybody know what a salt is? Anything about a salt? Anybody like to use salt on their food? Okay, what is it? Okay, let's write that up here. Okay. Anything, what's that composed of? Sodium, okay. Sodium is it a metal or a non-metal? It's in group 1. It's on the left side of the stair step. It's okay, we need to review this. Okay, on the left side of the stair step, there's our stair step. All those are metals. 80% of our table is metals. Okay, on the right of the stair step, 20% over here, those are non-metals. Okay, so is sodium a metal or a non-metal? So, what about chlorine? So do you think it's safe to say that a salt's composed of a metal and a non-metal? Yeah. Okay. We're going to look at all various different salts, so it's going to change, but the thing that's going to stay the same is it's composed of a metal and a non-metal. Okay. If we were to label our metals and non-metals, so the chart that I handed you or the little table there, okay, do your metals form plus charges or negative charges? Plus. Okay, metals want to lose electrons, right? Okay, so Sodium wants to lose one electron so that it can be like neon, the nearest noble gas. Okay? So we call things that form positive charges, don't we call these cations? Okay? Right? And the nonmetals, they want to gain electrons, right? Okay, so we often call these anions. Okay. So a salt is composed of a cation and an anion. Okay. Our complex definition is that a reaction of an acid and a base, okay, forms a salt. Okay. And this salt contains the cation characteristic of the base, okay, and the anion characteristic of the acid. Okay, so let's look at this. Oops. So let's take this definition and let's predict the product. Okay? We know we're going to form a salt. Okay? Water is usually formed, but not always. Okay? In this scenario, it will be formed. Okay? But it's not always formed. Okay? So let's label our acid and base here. Okay? So HCl is acid, and AOH is base. Okay? All right. Our acid's going to, exactly. Okay. Notice how I'm showing it here to the OH. Okay. All right. So when this is donated over here, what are we left with? Okay. For right now, okay, we're going to combine this, but we get that, right? Okay. What about over here? What do we form? Okay, that's what you, yes? Okay. So we really formed water though, right? We added a hydrogen to this OH. So we formed water. But we still have that, right? Okay. Why do I have a plus charge on sodium? Look at your chart. What ion does sodium form? It's in group 1. It always forms a +1, right? Okay. Our definition says we take an acid and a base, we form a salt plus water. Okay, so here's our water. And then it says our cation of the base. Okay, so if we look at our base, what's our cation? Na, right? Okay, it says that our salt is going to be characteristic. It's going to be cation of the base and the anion of the acid that combine. Okay? So if we have these two and we have a negative and positive charge, don't you think they're going to want to attract? Exactly. And so you form NaCl plus H2O. Okay? And we're going to be doing lots of these, but these get people every time, okay? Because you want to add that. And exactly what Aaron said, that would make sense. You'd probably just want to put NaOH2, right? Okay, but in reality, when this just gained a proton, okay, you formed water, and so you have sodium ion and chloride floating around in solution, which are then going to be attracted to each other, okay? Exactly, yep. Yep, and so this, we know, formed the chloride. Okay, and then here, so yeah, you form OH2, okay, and it's got kind of, okay, so instead of being a positive there, it's going to be neutral because you just formed H2O. so we'll practice these a lot. Okay. So there's two really types of reactions that you're going to have to be able to predict products and do like we just did here. Okay, we call this our molecular equation. Okay. What that means is that I took those ions and I put them together and that it's neutral, right? We don't see any charge here. Okay. The other type of equation we're going to look at is called the ionic or the net ionic equation. So we want to look at what ions are actually present in this reaction. Okay? So we're going to do a series of kind of go through some rules and talk through this, okay, for an ionic equation. Okay, so the first thing, if we look at scenarios that we could have a strong acid and a strong base react together, right? HCl and AOH was an example. Okay, we could have a weak acid and a strong base react, or a weak acid and a weak base, or a strong acid and a weak base. Okay, so there's different scenarios. Okay, so it's going to be important that you use your list and label things as strong or weak. Okay, this right here is also extremely important to our rules, probably even more important than this, is that we have three substances that completely ionize. Okay, so what do I mean by that? As we talked about before class got started. Okay, it's not gone, but it means that we form the ions exclusively, right? So it means that we get 100%. So if we look at HCl in water, we get 100% conversion. Oops. To this. Okay, so when I take HCl and I dilute it with water, this is what is in my flask or whatever my container is. Okay, is the chloride and the H3O+. Okay, there are three things that completely dissociate, meaning they form their ions: a strong acid, a strong base. Okay, that makes sense, right? That's what makes them strong on your list, meaning that they completely react, okay, in water to form their constituent ions. And also salts, okay? In this chapter, all of our salts, okay, so what do I mean by salt? What's a salt? Right here. The metal and nonmetal, where we have the cation characteristic of the base and the anion characteristic of the acid. Okay, in this chapter, and really for this unit, all the salts that we make can ionize. Okay, so just remember that as we're going through this. Okay, if you form water, okay, I'm just giving you the rules before we start this. It may not make too much sense right now, but you do not ionize water. Okay, so you're not going to try to break it apart and ionize it. This slide right here will be very helpful when you're doing problems. You can come back and check your, make sure you followed these rules here. Okay. Here's our first scenario. We said we could have a strong acid and a strong base, right, that could react. Okay. This is going to form a salt plus water. And we've said already that our salts are all soluble. So it's going to form a soluble salt. Okay. Okay. So let's look at this. Here we've got HBr. Okay. Is calcium hydroxide on your strong base list? CaOH2. Okay. All right. Okay, if you had to predict this product, do you think you could without it being up there? Okay. Notice we have to balance the equation, right? So we have to put a 2 and a 2 here for it to be balanced. Right. So HBr is going to donate a proton right here. Okay? So we have 2 hydroxides. Okay? So if we donate both of those protons, we're going to form 2 waters, right? Okay, then we would have calcium. So calcium, okay, what charge does it have? Anybody? +2. Okay, these are also on your list you've got there. Okay. Okay, and then we would form our bromide would be left in solution as well. Okay. All right, if you had me for Chem 111 and we learned to write formulas and name, we did a little trick called swap the states. Okay, so if you have your 2 ions there, okay, then the 1 goes here and the 2 goes there, and you get CaBr2. Okay. So there's our salt, right? Our salt has the cation characteristic of the base and the anion characteristic, meaning the nonmetal here, of the acid. So that's what makes our salt. Okay, so if you look at NaCl, it's got a salt. Okay, we have a salt, metal, nonmetal, metal, nonmetal. Okay, so that's our salt. It's just a different one. Okay. If you have a strong acid and strong base, okay, our rule said that a strong acid and a strong base completely ionize. So what you're going to do to get a net ionic equation is you're going to break apart your strong base and your strong acid into their ions. Okay? This goes back a lot to Chem 111, so you may need to go back and review. If we have time, we can maybe at some point or next Tuesday after going over the exam. Okay, but when you look at this one, I gave you this right here. Okay, these on top, you should know these. This is from Chem 111. Okay, a metal in group 1, 2, or 3 always forms a 1, 2, 3 charge. Okay, the nonmetals. Okay, so your halides there, they form a -1 because they're 1 electron away. Okay, and then group 6 forms a -2 because it's 2 electrons away from being like the nearest noble gas. Okay, so if you need to go back and review Chem 111, I would suggest it. Okay, at the bottom here, we have polyatomic ions, right? You'll be given this list on your exam, okay? But it doesn't mean not to look at it. You still need to be able to use it properly. Okay, so if you look down here, a polyatomic ion is a group of atoms that has a charge, right? So we have phosphate, sulfate, sulfite, phosphite, hydroxides even on here, which we already know is OH-. Okay, so you're going to need this in order to break apart your acid and base into the ions. Okay, so HBr is a strong acid. Does everybody agree with that? You see it on the first thing you'd have to do is look and see, am I dealing with a strong acid or a weak acid, a strong base or a weak base? Okay, so if we look over here, we see HBr, strong, calcium hydroxide, strong. Okay, our rule says that we break these apart. Okay, a hydrogen of an acid always is going to form H+, because that's what an acid is, right? It's H+ or H3O+, but it's a lot easier for us to look at it like this. Okay, so we just have a hydrogen. Okay, we have a 2 as a coefficient, so we're going to form 2H+. Okay, and then we break out our bromine, which is in group 7, and forms a -1 charge, right? Okay, and we have 2 of them. So we have 2 bromide, Br-. Okay. All right, does everybody see how that was broken apart there? Okay, you take HBr, and because it completely ionizes, remember we said that earlier, we have that 100% conversion, okay? We're trying to find out what's our net ions are in solution. Ion means a cation or an anion, right? So you break this apart. If I break this apart, okay, a hydrogen of an acid is always going to form H+, right? Because it's an acid, okay? and it forms a proton, and it's a proton donor, right? Okay. If we break apart and we have 2, because in our equation we have a 2 out front, right? So we've got to have 2 here. We've got to keep our equation balanced. Okay. The bromine, if it breaks apart into its own ion, we know that bromine always forms a -1, right? So we form +2. Okay, and we still have 2 because remember our coefficient out front means we have 2 hydrogens and 2 bromines. Yes. Yeah, if there was just a 1, you just have a 1 there. Yep. Okay. All right. So our rule says we can break apart, meaning ionize strong acids and strong bases. All right, next is calcium hydroxide, which is a strong base. All right? How many calcium atoms do we have? We just have 1, right? Okay. So if we pull out that calcium atom, what's its charge going to be? 2+, because it's in group 2. Okay. If you don't remember this, look at your chart, okay, that I gave you. Okay. There we go. Right. And then we have OH, which is what? If it's an ion, what do we call it? Hydroxide, right? And it's on your polyatomic ion list there. Okay, it's OH negative. Okay, and then how many do we have of those hydroxides? 2. So we would say +2 hydroxide. Yep, you have to pull it. If you're ionizing it, that's what we're doing. We're taking a molecular equation where it was just neutral, and we're pulling it into its ion. So everything is going to have an ion except water. Remember on that slide, those rules, water does not ionize. So you just leave it as it is. You just bring it down. Okay. So here we have a product. Okay, what's the calcium bromide there? What's it called? Is it an acid? Is it a base? What is it? It's composed of a metal and a nonmetal. The salt. Okay. In our rules, do salts ionize? Yes. Okay. So we're going to take our salt and we're going to do the same thing. So we're going to, I wish I had more board space. Let me come down here. Okay. So I'm just going to rewrite this here. Okay, so we broke apart our acid and our base. Okay, now we can ionize the salt. Okay, so if we have a calcium, when we just have 1, and it ionizes, it's going to form Ca2+. Okay. And we have 2 bromines. Everybody see that? We have the Br2 there. Okay, so we're going to form 2 Br minus, right? Okay. Right, and then we take water. We don't do anything to it. All you're going to do is bring it down. Okay, so when I mean bring it down, just bring it into your next step here. Okay. This is what we call taking a molecular equation. So our first one up here is molecular. There's no charge in it. Okay. And we break it into an ionic equation. Okay? Okay, but when you use the word net, what do you think of? Like I have a net amount in my bank account. Okay? So that's what you actually are going to have out of your equation, your net ions. So the last step is to cancel out like terms on either side of the equation. Okay? So if we look here, we have 2H+. Do we have anything that matches that over here? No. All right, what about 2 bromide? Yeah. Okay, what about Ca2+, calcium ion? Okay. Do you see anything else? Okay. So if we bring down just our net, okay, what wasn't canceled, we get 2H plus 2 hydroxide yields 2H2O. So if you take a strong acid and a strong base, okay, the net ionic equation is basically just H plus, which is our definition of an acid, right? Hydroxide, which is our definition of a base, yields water. Okay? Yes. Okay, so let me pull this down just to show. So I just did all that on the board, but okay, here's our net ionic equation. Okay? Or you can just write it as, you know, cancel out your 2's there, because they could all essentially you divide by 2 there. Okay. This scenario, when you have a strong acid or a strong base, the net ionic equation is always the same, meaning it's always going to be H plus hydroxide yields water. Okay. This is our only scenario. So by scenario, I mean if we change it to where now we have a weak acid and a strong base, then this isn't going to happen every time. Okay? Let's do it one again. Some of y'all still look a little bit confused. Okay. All right, y'all pick a strong acid and strong base. One that's different, so hydrochloric acid, okay. Okay, if you can't see, you may want to get it to where you can. That's the only place I've got. Okay. HCl, okay. Strong base. Okay. Perfect. Okay. Exactly. Yep. So that's what you're producing. So that's why a lot of times in the lab it doesn't really matter if we want to produce, you know, this where we have our acid and base yield water. I mean, we can use, you know, any strong acid, strong base. Okay. And right now, not all salts are soluble. So this later will change, but for the ones right now, every salt is going to ionize like we did. Okay, first thing, so you're going to have to be able to do 2 things. And like I said, we're going to practice these whatever remaining time we have today, and we'll practice them on Tuesday. So we'll spend a good bit of time on these. All right, but first thing is we want to predict our molecular equation, meaning we don't have ions. Okay, so if we were to predict our molecular equation, so take a second, I want you to try to predict it. Okay, you know you're going to form a salt and possibly water. Do what now? No. I'm actually going to go ahead and just pull this up so you'll see. Okay. Once you get a hang of the net one at ionic, sometimes these are harder for students for some reason. What I would do, honestly, this is what I do. I still think of it as, you know, a proton donor, proton acceptor. But I find my salt. I mean, that's the easiest thing. Look for your metal. You're only going to have one that's going to be in there. So here's your metal. And then what's my nonmetal from the acid? It's a chloride. Okay, so what's my salt going to be? Lithium chloride. Yeah. Okay. And then what's left over? Water, right? It donated a proton, so I get plus water. Okay. All right, we have a strong acid, strong base, and a salt. We know that all 3 of these ionize. Water does not. That's a common, a couple people for some reason will try to ionize this. even in other examples as we go along, and it gets them all out of whack. So do not ionize that. Okay, if we ionize HCl, okay, first off, is everything balanced? We've got two hydrogens, one lithium, one chlorine, one oxygen. Looks good to me. Okay? All right, so if we ionize this, what are we going to get, Damien? You can do it. Yep. Okay. What's the acid all? Okay, very good. Plus, okay, Cl, but what's its charge? Okay, -1, right? Okay. All right, Jeremy, what's going to happen with our base? So we've got our acid dissociated, broken apart. Okay, what's our base? How are we going to break it down? Okay, but what's ours? Not just lithium. We have to put a charge. What's our charge? +1. Okay, and then hydroxide's always the -1, right? Very good. Okay. Sion, how's our salt going to break down? Okay, you got to look at it. How's it going to break? It's going to break right here, right? If you think about it that way. What's that going to become? Very good. All right, and Justice, am I going to break down water? Okay. See if else I can. All right, Martin, give me one like term that I'm going to cancel out. Okay. Okay, Jennifer, give me another one. Okay. Is that it, Michael? Yes? Okay. And Breck, what's my final answer going to be? Which is exactly what we said it was going to be, right? Okay, so here it is right here, if you can still see it. Okay, so strong acid, strong base scenario always ends up as a net ionic equation of H plus hydroxide yields water. Okay, this is the only scenario where it's always the same. Okay, so our other scenarios will be different. Okay, if we have something that won't completely dissociate. Okay, so let's say I gave you acetic acid. Okay, is it on your list? Okay, let's see what time it is. If we have time to do this or not. Okay, is acetic acid on your strong acid list? No, it's a weak. Okay, so this is where it becomes really important that, I know it seems very simple, but that you can use your list. Okay, so if it's not on there, it's assumed to be weak. All right, so here is an example. Now we've changed. We have a weak acid. Okay, so everybody look, do you have nitrous acid on your list? No. Okay, plus NaOH. Okay, is NaOH weak or strong? It's strong. Okay, look at your list. Strong. Yeah. Okay. Here's our equation. So one thing you can do when you're studying is go back and be sure you can predict this product right here. Okay. There's your metal and nonmetal. Okay, this time your nonmetal is a polyatomic ion, right? So if you look at your polyatomic ion list down there at nitrite, I believe it is, yeah, it's got a -1 charge. Okay, so here's molecular, no ions. All right, of these compounds, what's going to ionize? What was our rule? Okay, is this my salt? It is. Remember, this is a nonmetal. It's a polyatomic ion. Okay, so the salt is going to ionize. Okay, Justice already said the water is not, right? Okay, so we're going to break this down. Okay, what about NaOH? Will it ionize? Okay, it's on our list, right, of the 3 things that ionize: strong acid, strong base, and salt. Okay, what about this? Is it going to? Nope, because it's weak. Okay, so all you do is the same thing. Okay, here's your reminder of the 3 types of substances that ionize: strong acid, strong base, salt. Okay, here's our equation. Okay, if it doesn't ionize completely, meaning here it's a weak acid, all you do is bring it down here as is. Okay, you don't split it apart or dissociate it. Okay, then you move on to the next. NaOH is going to break down into Na plus hydroxide. Okay, you cannot forget, don't forget, when you ionize, you have to have a charge with that cation or anion that you write down. Okay, what about our salt? Okay, we know that the sodium forms a +1, so we've used that 3 or 4 times, right? So it has a +1. Okay, where did I get this charge? How do I know that NO2 has a -1 charge? Yes, this is where you have to recognize that this is a polyatomic ion. Look at your list, go down to the nitrite, and NO2 has a -1 charge. So there it is, and then here is the water carried down. All right, this time we're not going to have as many things to cancel out, but we're going to show it anyways. Okay, so I'm still looking here. All right, what's my common term that I could cancel out? Exactly. So I can cancel it. So I just simply bring this down, and this down. Okay. So my net ionic equation, this is one of hundreds of examples. Okay. When you go to these scenarios, they're all going to be different. Okay. So our first scenario, strong acid, strong base, is the only one where we get the same thing every time. Okay. And we saw how we did that because everything cancels, and you're just left with the H plus hydroxide yields water. But here you're going to be left with this. Okay, but if it was a different weak acid, so if it was acetic acid, then you'd be left with acetic acid. So it's different depending on what the weak acid is. And so this now is our net ionic equation. Do it now? Do it now? Of breaking it down to the ions? Yeah, this tells you what, yeah, it can tell you that, but it tells you what your actual, ions. So when you make a solution, what component of it is going to actually be reactive? Okay, so the sodium, it canceled out, right? So it's not really important to us. Okay, if I needed sodium as a reactant, then that's not the way I'm going to do it. Okay. But this is what's your reactive component. So if you mix these two together, these are your ions that are actually floating around in your solution. Okay, and they make it either acidic or basic, and we can base a lot of things off of these numbers. But just to give you an example, if I made this solution, I can take this And we bring this into organic chemistry, and then from this we start doing tons of reactions with these equations. Because now I have this negative charge here. I can take that hydroxide and react it with another acid, and it can do reactions. Okay, so you have to know what your net ions are to be able to know how is it going to react if I put something else in there. Okay, does that make sense? Yeah, a lot of this is just stepping stones for what you might see later. So it's hard to get to the, I can't in one semester get to, everything and show you how it's all used. I wish I could, but yeah, you have to know this in order for you to be able to use a solution, because this is really just an acid-based solution. So if I want to know how to use it or what I'm really forming, if it just neutralizes, then there's no, it's not going to be able to be used. Okay, so you have to know what ions. We actually call this a nucleophile, so we use that to react with other starting materials in organic. So that's how it is used. We'll look at the other two scenarios, so they're very similar. Please look at your notes so when you come back on Tuesday, you didn't forget everything we talked about, because we'll pick up with the last two scenarios, so weak acid, weak base, and our weak base, strong acid. So y'all have a good weekend, and I will see you Tuesday, and at 1 o'clock if you want to go over the exam, ask questions, anything like that on Tuesday, you can. Yes? Tuesday, yeah, during lab time, so we would already be. Yes. Yes.
Later you said
Yes, it's different. Yes, it is confusing. Yes, but the reason it's different is because you're looking at binary acids versus a ternary acid here. Let me turn my recording off real fast now.